Alright, here we go. AP problem 0002. Um, so this is a wonderful gas law problem. And it's actually really three problems in one. So here we'll start right from the top. Determine the empirical formula of a hydrocarbon that contains 85.7% carbon by mass. So we're looking for the formula for some CXHY. Now I know there's no O or N's or anything because if it doesn't give you any information, you just assume that it's hydrogen and carbon. Um, so if you start with, if you know there's 85% carbon, that means the remaining 14.3% must be hydrogen. With these empirical formula problems, remember, go to assuming there's 100 grams. Let's just say that there's 85.7 grams of carbon and there is 14.3 grams of H. At 12 grams per mole for carbon and I'll go 1.01 grams per mole for hydrogen. That's going to give us, I'm going to skip right down to here, that's going to give us 7.14 moles of carbon and 14.2 moles of H. Now, to find empirical formula, you got to find the mole-to-mole ratios here. So we're just going to divide by the smaller number. So 7.14 for carbon and then 7.14 here, which gives us a 2-to-1 ratio. So I have 1 carbon for every 2 hydrogens. Now this is empirical formula. So I don't know anything more than that right now. But we're going to actually end up figuring out molecular formula here in a minute. So I'm always good habit to get into, box your answers, okay, when you're doing these, so then that way the AP people don't have any trouble finding it. Okay, so going into the next problem here, I'll do this one in blue just to keep the two sections separate. B is related. So the density of a hydrocarbon in part A is 2.0 grams per liter at 50 degrees Celsius, 0.94 atm. So we're clearly looking at some sort of PV equals nRT problem here. We're not changing state, it's just one state. So let's see if we can put that together. Now we've got a few things. They're going to give us density. We've got some T, we've got P, and we're looking for molar mass. So this is one of those problems where we're going to have to push all the equations together. So let's go here. We'll go part B. We've got PV equals nRT. We've got T. We've got P. We need molar mass, which is the number of grams per mole, and then we have density, which is mass over volume. Now we're missing N and V over here, but we have them through this. So I'm going to resolve this guy for N. N is mass over molar mass. Okay, and we're gonna plug that in there, and then to replace the volume we don't know, we're gonna use the density equation. V equals mass over density, and we're gonna plug that guy in over here. Now when we get this all plugged in, okay, I'm gonna do it right over here on the side. We've got P times M over D is equal to mass over molar mass times RT. Now, if I divide both sides by M, I'm actually going to be able to get rid of that. Okay, so let's come in here. I'm going to divide both sides by M so we can get rid of that. And then, come on. Oh, there I am. That's actually going to get rid of that by dividing both sides by M. And then let's get molar mass by itself here. So I need to multiply both sides by D and divide both sides by P as well. Okay, that'll all come out in the wash here, and we should end up with molar mass is equal to density over pressure times RT. Okay. Oh, we had to also multiply both sides by molar mass to get to that in the top. molar mass. So that's going to cancel that there. Everything else is left over. Or mass gets already been canceled out. We took care of that already. Density cancels, pressure cancels. I'm left with molar mass times RTD over P. So now all we have to do is come in and plug all the numbers in. So let's just rewrite that one more time. Molar mass equals dRT over P. Now I really suggest pushing the variables together before you try to plug numbers in. Okay. So in this case, we know that density is 2.0 grams per liter. I'm going to skip over T. So T was, if we come back up here, 50 degrees C, but we have to use Kelvin, so that's going to be 323 Kelvin. So 323 K. And then pressure, we're going to put that in the bottom of this one, and pressure in this case was 0.948 ATM. 0.948 ATM. And then R is going to be the one that cancels ATMs and Kelvin, so we're going to need the 0.08206 liter atmospheres per mole Kelvin in this case. Now, before I crunch any numbers, let's make sure all my units cancel. We don't want anything left over. K is gone. Atoms are gone. Or I'm sorry, ATMs are gone. Liters are gone. But that leaves me with grams per mole, which is convenient being that we're trying to solve for molar mass. So we'll push, so we run these through the calculator here. We'll get a calculator. 2 times 323 times 0.08206 divided by 0.948 is not that. I must have missed the decimal place in there. Let's try that again. 2 times 323 times 0.08206 divided by 0.948. Oh, looks like a much more reasonable number here. So molar mass ends up being, there I am. Molar mass is going to end up being 56 grams per mole with the proper number of significant figures. Now, this was just part of part B. That's molar mass. Now we have to determine the molecular formula. So this is going to tie back to what we found in part A. We know that the empirical formula is CH2. So if we figure out the mass, that's 12 plus 1 plus 1, that's 14. So we just need to figure out how many times 14 fits into 56. So you divide that away, and it's going to turn out to be 4. So I just need to multiply all my coefficients here by 4. I'm not my coefficients, but my subscripts. So our compound is C4H. Come on, H8, which is it turns out to be, that'd be butene, but that's irregardless here. So that's part II. This was part I, and we've solved another part. Awesome. So we're moving right along here. That was probably one of the more challenging parts of this. So we'll just give that a nice little box so we can figure out that's part I and that's part II. Wonderful. All right, C. C is a 2-flask problem. Now it turns out, if you've already read this, you'll know that this is completely separate from that problem. So now we're looking at 2 containers connected by a stopcock. The problem doesn't state it, but we'll assume that the tube here in between has no volume, which is not true, but it'll work. The 5-liter flask has a pressure of 3 atm, and the smaller one appears to have a 0.55 atm pressure. Now, there's 2 ways to approach this. You can find N using PV equals nRT for the CH4, and then we can find N for the C4H6, add them together and use PV equals nRT for the total volume. Or what's going to end up being less math, a little less work, is just saying, what if I took this gas and expanded it to, instead of being 5 liters, make it 6? And what if we we expanded it into an empty flask? And it's not empty, but doesn't matter because it's all ideal. Then we do the same thing with this flask. We say, okay, everything in this flask expands into an empty flask, and it goes to 6 milliliters. And we'll find pressure for CH4 after the stopcock's been open, and find pressure for C4H6 after, and then we'll just add them together using Dalton's law. So let's run that. Okay, so we'll come down here, and let's get a little more space. Where's that space? There we go. Here, whoop, whoop, whoop. Yeah, that'll look. All right, so part C. And remember, this is independent of that part A and B, so we're kind of doing a new problem here. So combined gas law, P1V1 over N1T1 equals P2V2 over N2T2. Now we're not changing the number of moles, and we're not changing temperature. So we're really just looking at Boyle's law here. Yeah, Boyle's law. So, and we're going to be solving for the pressure after the gas has been expanded. So we're going to go P2 equals P1V1 over V2. So let's do the CH4 side first. Okay. Pressure 1 was, we better really make sure I get that right. 3 ATM with 5 liters. Okay, so we'll come back down here. So we're looking at 3.0 ATM in times the 5 liters that it started at. And then once we open the stopcock, if we come back up here, it'll be 5 plus the 1. This is a typo, by the way. That shouldn't be there. So we're looking at a 6.0 once it's expanded. Now we'll do the same thing down here. We'll do it for C4H6. In this case, we've started with 0.55 ATM in 1 liter of space, and then we're going to expand that into that same 6 liter volume again, which is going to give us some different numbers. So now, this will give us, and this will give us PCH4, and this will give us PC4H6. Add those two together, and we'll be in good shape. So crunch the numbers here. Let's get that calculator back again. Clear that out. 3 times 5 divided by 6, 2.5. So 2.5 ATM plus, clear that out, 0.55 times 1 divided by 6, 0.092. Okay, so 0.092 ATM. Now watch your sig figs here. Tenths, hundredths. So this 9 is actually going to affect this very little, and we're going to end up with a number that looks like 2.6 ATM for P total inside the flask after the stopcock has been opened. Awesome. Okay, so that's C in a nutshell. And you can see there's a lot left. Now, like I said, you could have approached this from the perspective of a P2, where you would do PV equals nRT, solve it for N for both flasks, and then do a PV equals nRT after, and that would give you the correct answer, but it's going to be way more math, way more units, and not nearly as simple. So let's not go there. We'll just pretend that's not there. All right. All right, C's done. Let's make sure we've answered the question. Assume the temperature remains constant. What is the total pressure of the system? And it didn't specify units, so ATM's in good shape. A's done, B's done. So the last one we have is D. Octane, so this is another completely independent problem. Octane has a density of that at 10 degrees C. I'm going to put an emphasis on that because this is actually going to throw a trick, extra step in this problem. And then it says a 255 milliliter sample of C8A18 measured at 20 degrees C reacts completely with excess oxygen as represented by the equation below. How many moles of gaseous product are formed? So we're going to ask it how much of that and how much of that are going to form when this thing is all said and done. Given an unlimited amount of this, okay, so I need to know N for C8A18. Well, I can find grams from milliliters, but the problem is this is grams per milliliter at 10 degrees Celsius, and we have 255 milliliters at 20 degrees Celsius. So what we need to do is adjust the volume here, okay? So I'm going to scroll back down here, okay? We're going to do new section again. Part D. We have, this is another one of those changing condition problems. So we're looking at combined gas law one more time here, P2V2 over N2T2. But in this case, temperature is not constant. We'll assume pressure is, and we'll assume the number of moles isn't changing, so we're really looking at a V1 T1 equals V2 T2 problem over T2 problem, where we need to know V2. So we need V1 times T2 over T1. Plugging in our numbers here, our volume to start is 255 milliliters, okay, which is great and all, but and then our T final, the T that we're trying to adjust to is 20 degrees Celsius, okay, but we can't use 20 degrees Celsius, we have to use 270, the Kelvin version here, so 273 plus 20, 293 Kelvin over the 10 degrees, which is what we need to compare it. Oh, do I have that upside down? So we need it to be at 10 degrees. It's at 20 degrees. So T1 is actually 273. My mistake, 273 Kelvin. And T2 is going to be the one. This is what we want to be the 293, 283 Kelvin. Okay, so we'll run that number to get the adjusted volume, because we need that volume that we can compare to that density number, because we need to get grams. So we'll get that calculator pulled up again. We're looking at 255 times 283 divided by 293. I keep doing that. So the volume is actually, lost the number, going to be 246, okay? So we're looking at about, this would be an easy place to make a mistake on the test. So this is the volume at 10 degrees C. Now we remember, we're trying to find the amount of stuff here and here. So we have to get N. And to get N, we need to find G. So we're going to use density here. We know volume. So our 246 milliliters, and we know that each milliliter weighs 0.0703 grams. Okay. Okay, so we'll run the number there. 246 times 0.0703 gives us 17.3. 17.3 grams of this octane. Okay. We need to get moles, so we got 8 times 12 plus 18. Each one, we'll just say that one weighs 1. That's 96 plus 18. It's about 114 grams per mole. So once again, back to our calculator, divide that out by 114. Now you'll notice that I'm not clearing out my calculator every time. I'm showing my work, but I'm saving myself the hassle of retyping this stuff in. So we're looking at number of moles as being 0.15, oop, lost the number again, 0.152 equals 0.152 moles of C818. Okay, now that's great. That tells us how much of this we have, but we need to know these parts. Okay, remember, moles of gaseous product. So now we're diving into our good friend stoichiometry. We've got 2 problems to do. We have to do with a 1.52 moles of C8H18, but we're going to end up doing this twice, because one time we're going to find it's going to be moles of C8H18 over moles of H2O. And then our second one here is going to be the same thing, only the top's not going to be H2O, it's going to be the CO2, because we have to find both parts. Over moles of CO2. Now we got to make sure our coefficients are right. 2 for the C18, it's 16 for CO2, and 18 for water. Let's come back down here. This is 18 to 2, and this is going to be 16 to 2. Okay. So back to our calculator here, I'm going to go ahead and clear this time, 0.152 times 18 divided by 2 gives us 1.37. moles of H2. Oh, actually, was that point? Yep, that was right. So then we're going to go 0.152 times 16 divided by another 2, so 1.22. Okay. So 1.22 moles of carbon dioxide. Add those together, we're looking at 2.59 moles of gaseous product. And once again, we have our answer. We give that nice little box. This is our answer to part D. Awesome. So at this point, we've solved them all. This is a pretty lengthy problem. This would be a long 15-minute AP problem, but it would definitely be in the realms. And I've shown the work and I've explained things a little more thoroughly. But the hope is you'd be able to roll through these problems pretty quick. Okay. So one more time here, I'll scroll from the top down real nice and slow so you can check. You can see the final answers here in the last 20 seconds of the video.